So now that you're all burnt out on compactness and maximum stuff, we'll take a short break and do some linear algebra for fun. So I want to talk today about quadratic functions. Now, for reasons that are historical that I do not know precisely, mathematicians have been calling these quadratic functions quadratic forms. The word form gets used in the context of linear and multilinear algebra a lot. So this is just a fancy word for functions. Completing the square. And eventually we'll tie this back to the calculus stuff. So I gave you the clue why we're doing this at the very end of lecture yesterday. I reminded you that there was Taylor's formula that you knew for single variable calculus, and we saw that the second derivative was determining what the function did near a critical point. We're going to have an analogous formula in the multivariable case that's built on these quadratic functions that we're now studying. So if I, for example, gave you suppose I gave you, and for fun we can actually practice writing script Q for quadratic. If you don't like script Q's, you can call them regular Q's or F's or whatever. But I did that just to annoy Dan.
Two, yeah.
It is not a 2, it's a script Q.
It's a 2.
So if I gave you that quadratic function, and I asked you, what does it look like? Everybody in the room knows what that looks like. The graph looks like a... The graph of that function.
Looks like a
paraboloid going up. What does this piece look like? The xy part. It's a saddle, right?
Yeah.
Yeah.
So, but what do you get when you put them together? And no, this isn't a, what did you get when the aardvark crossed the road joke? Who knows? So, you're supposed to have some inkling from high school algebra that you could try to complete the square. Now you haven't completed the square with so many letters in it, but if y were a number, you would know how to complete the square. Here's what I'm going to suggest. You want to write it this way, and you want to say to yourself, what term could I add to this so that this would be a perfect square?
Something over 4. Y over 4. Y over 2 squared.
So, so I'm going to leave myself a little room on the next line. So I'm going to say x minus what squared. We'll start off with x squared minus xy.
Y over 2.
Y over 2. So if I do x minus y over 2 quantity squared, I get x squared minus twice x y over 2, so that's minus xy, plus y squared over 4. Well, I don't want y squared over 4, so I'll subtract it off, and then I haven't changed what I had, and then I'll add my y squared back. You guys follow that?
Yeah.
That's completing the square. And so what have I got now? I've got that this original quadratic function is a square of this linear polynomial, and then what's left over? 3/4 of y squared. Now can you tell me what the graph of this surface looks like? The graph of that function as a surface, what does it look like?
You think it would still be an ellipse?
It it's a positive something or other squared plus a positive something or other else squared.
So it's a parabola.
So it's still some sort of sheared paraboloid, yeah. But what you have established, without even trying to identify graphically what this is, that this quantity, unless this is 0 and this is 0, it's always going to be positive, because it's a sum of squares with positive coefficients. So we observe that q of xy is positive unless both these terms are 0. X minus y over 2 and y are both 0, i.e. unless what?
X and Y are both 0.
X and y are both 0. So except at the origin, that function's always positive. Okay, let's do another example. Three x squared plus minus 12xy plus 11y squared. So I want you to practice your algebra skills. How do we complete the square for this? Again, you want to concentrate on the first two terms and leave the y squared for later.
Well, we can take out the
Background.
Take out a 3 from the first two terms. Four xy. And then 11y squared just is coming along for the right so far. What am I going to do on this piece? Well, I'm going to do what I did before. Can you write this as a perfect square, but then correct it?
So yeah, it's x minus 2 minus, that's squared.
Plus
Okay, so if you square x minus 2y, you get x squared minus 4xy plus 4y squared.
So subtract 4.
So I better subtract off the 4y squared because I don't want to change my function. You may have remembered completing the square in high school where you added stuff to both sides of an equation, but here I'm working with a function, I don't have an equation.
You're adding to the same thing.
So I'm adding a clever 0 here. This is equal to this. And then I still have my 11y squared. All right, now I go back and I say, all right, 3 times this quantity, and then what? Minus 1y squared. So what do you conclude about this creature?
Did you have the one? Because you have minus 12.
I have minus
Oh, right,
12
yeah, okay.
plus 11. So this is going to be going up in some directions
Down.
and going down in the y direction. So it's going to be satellite, right? Something squared minus something squared is satelish. Okay. So this is going to be useful once we bring in the calculus to find out that second order term in the Taylor's theories, in the Taylor's polynomial creature, because that's going to help us decide what's happening near a critical point. But before I get the connection to the calculus, I want to show you a linear algebra way of approaching this that isn't a high school algebra way. In come symmetric matrices. I want to write my quadratic form, so that's this quadratic function. Now, I'm going to put it in vector notation at the moment, script q of a vector x. So this is my vector x. How can I do linear algebra when there's squares?
Set some variable equal to each.
So say like a is x
Can't.
minus y over 2 squared and b is 1.
No, but
You
it
can
has to be
substitute.
linear. So
You can substitute.
Capital A equals.
So I want to put a matrix A multiplied by x, and then to make it quadratic, I'm going to dot the whole thing with x. Now, some people might like to notice that I could write it, remember our dot product can be written using the transpose. Right? If you transpose this x and put it in front, you're then taking x times vector ax, and that's doing this dot product. But I want to make sure my A is symmetric for reasons that will become clearer and clearer. So this is your charge. Take this formula as one example, and take this formula as one example, and tell me what the matrix A is going to be. So in the first example, I want to think about taking xy and dotting it with mystery matrix times xy and getting x squared minus xy plus y squared. So let's think about that. How am I going to get x squared from this?
You have to have a 1.
The only way I'm going to get an x squared
Top left is 1.
is from the first coordinate.
Right.
So how am I going to get an x squared from, I have an x times this stuff, how am I going to get 1x squared?
Put a 1 in the left.
Put a 1 there.
There you go.
Then I'll have 1x plus some number of y's times x, that'll give 1x squared.
Mine will put a negative.
Now let's fix the y squared while we're at it.
Same thing.
Same thing down here, agreed?
Right.
Because then I'll have y times some number of x's plus 1y.
Negative a half.
-1/2.
Now, what goes in the corners?
Negative a half.
Yeah, it's symmetric.
Let's see, if we want it symmetric, so you've got to split this term into two pieces that are equal. What pieces do I want? Well, x times how many y's, and then y times how many x's, as long as the how many's are the same, I should split that in two pieces. So this should be minus a half, minus a half. It's a little hard to read because of all the erasing. Does that check? If you're having trouble following what I'm gesturing here, do this matrix product, and you get 1x minus a half y, and then you get minus a half x plus y, and now dot it with xy, and then you see it, right? You get x squared minus half xy minus half xy plus y squared. Here's my symmetric matrix for that problem. You guys tell me what it is for the other one. In the second example,
Can we pull the 3 off? 3?
Isn't it minus 12?
I was going to check, but okay. Can you guess what matrix ought to go here?
3 negative 6.
3.
Negative 6. Negative 6. 11.
Everyone get it? What are you doing? You're putting the coefficients of the squares on the diagonal, and you're splitting the other off-diagonal term into two equal pieces. Well, so let's go back to chapter 4, because you guys miss it. And suppose I took this, I'm going to work with this matrix first just because it's got integers in it. Well, now I'll do that one first. Suppose I take this matrix and I try to put it in echelon form. So what do I do?
Keep the top the same.
add half of the first row to the second, add half of the first row to the second.
3/4 or something like that.
Now, I said echelon, didn't say reduced echelon. Now, do you remember the stuff we did when we talked about elementary matrices and how we could understand row operations in terms of multiplication by elementary matrices? Sort of. So, if I call this matrix U for upper triangular, as we did back in chapter 4 for a day or two, and I say this matrix is some elementary matrix times A, remember that that then said that I could get back A by taking E inverse times U. Remember that?
Yes.
And then the product of all those things we called E when we were talking about reducing to equal to echelon form. So what's my E here? In this case,
1, 0.
1/2.
is that right?
Yep.
What did we do? We kept the first row the same, and we added half the first row to the second row. So that's my E. So what's E inverse? No, you don't have to go through all the algorithms. You can just think. E inverse must correspond to doing the inverse elementary row operation. Leaving the first row alone, you still leave it alone. What do you do if you've added half the first row to the second? How do you undo that?
Subtract backwards.
And if you don't believe me, you can, in fact, multiply these and see their inverses of each other. Or you could do the algorithm for inverses if you prefer. So what do we have here? We have that A is E inverse times this upper triangular echelon matrix, which is this times this. And it sort of looks compelling. If there were a typo here, you might think that this matrix was the
Transpose.
transpose of that matrix. So suppose I want to call this L for lower triangular. And I want to write this as L and an L transpose on the other side. I'm going to need some matrix in the middle that will allow me to fudge that 3/4. Well, the matrix in the middle that will allow me to fudge the 3/4 is the diagonal matrix with 1 3/4. You don't believe me, you say. Well, let's check it. Put the 1, put the 3/4, and then put the transpose of L here. And let's actually multiply this out. Well, multiply these two together and think about it. The first row stays the same because of the 1 here. And what happens to the second row? Multiplies by 3/4. Well, and that is what I had up here. So by doing this factoring game here, I was able to split this matrix up into a diagonal matrix with constants times L transpose. Do the numbers that are showing up here look remotely familiar with what is
Up in the,
on the upper left board?
Yeah,
the coefficients there.
Up there, there's a minus a half y. Well, here's a minus a half. And then there's a 3/4 y squared. Well, there's a 3/4.
Oh, because, wow, that's weird.
We already had that in U though.
We did.
except for it was in a different location, I guess.
So now what I'm going to do before I reveal the inner secrets of why this is working. Let's do the second example. Let's try to write this guy in the form lower triangular diagonal, E for diagonal, times low L transpose. So let's try to now write the second matrix. I think Cameron has very bad memories of this particular stuff. Not due to Cameron, but due to me. Let's try to write this matrix A in the form LDL transpose, where again you're getting the L out of doing reduction to echelon form. So let's go for it. How do I reduce this guy to echelon form?
Add 2 times the first row to the second.
So I add twice the first row to the second, and I would get, so if I multiply by some elementary matrix, which you'll tell me in a minute, I end up with 3, -6, 0, -1. Now, what row operation did you tell me to do, Mallory? Add twice the first row to the second. So that's this, isn't it?
Yeah.
Not looking good. This doesn't look like good transpose of that at all. Not so much. Well, what should I be? Here I played a game of factoring stuff out into a diagonal matrix. What diagonal matrix do I want to factor out? Well, there's a 3 here, and there's a -1 here, and then what's left?
Which is actually the inverse, well, the transpose.
Which is, so remember we had to do the inverse here of the elementary matrix?
Except the Q is negative arrow.
So, in other words, my L should have been the inverse of this, which again switches the sign on the 2. And now, lo and behold, this is L transpose. So I have A is LDL transpose, where L is 1, -2, 1. And D is the diagonal matrix that enters 3 and -1. Say to yourself, do those numbers look familiar?
Yeah.
There's the 3 in front of the first term. There's the -1 in front of the y squared term. And then the combination of x minus 2y is coming from here. So let's see if we can actually write out the algebra that's saying what I'm hand waving.
Thanks.
All right, so let's look at x dotted with ax. And let's think of that as x transpose ax. And we've just written A substituting A is LDL transpose. What does this become if I put in that for A? X transpose LDL transpose X.
Oh, that's better than HDL transpose.
Now, some of you, you're all too young to worry about LDL cholesterol, but I'm not. Can you think of a regrouping?
XTL.
Yeah, XTL.
And what is X transpose L in terms of this?
The same. No? Yeah.
Remember Shusok? What's the transpose of a product? The product of the transposes in reverse order. That's X transpose L. Because L transpose transposes
Yeah.
L. So in other words, if I make in a minute I'm going to think of this as a change of variables, but is this not what that formula is looking like? What, in our case, in our second case, L is 1, -2, 1. So what is L transpose X? Well, transpose L, multiply by the X vector, and what do you have? So what happens if you take this vector and dot it with D, the diagonal matrix? What was D? It was 3, -1, times this vector.
You got it with 3 negative 1.
Well, no, I did transpose. I mean, thinking of dot is the same as putting it in here transposed. What do you get when you dot that? You get exactly what we had that I've now erased.
Yeah, you
I
erased it.
just erased it. This is 3 times x minus 2y squared plus -1 times y squared. So the magic of the completing the square is exactly putting stuff in echelon form. And the way you should think about this is that I'm starting with my original script Q that I'm trying to understand, and I'm saying if you make a substitution or a change of variables, you've diagonalized your quadratic function. If you let this be x prime and you let y be y prime, I'm saying in my new coordinates, this is x prime, and this is y prime. In my new coordinates, I have a quadratic function that's a sum of squares with the coefficients given by the entries of D. So the point of completing the square is that you've separated out the mixed xy terms and you've written it just as some number of x prime squareds plus some number of y prime squareds. Looking at that, you immediately know that it's going up in this direction, going down in that direction. You understand it. All right, well, are you feeling mystified?
Highly.
But I mean, this calculation shows you why the linear algebra is giving you exactly the completing the square that we did algebraically. This is exactly the combination we did to do the completing the square. And it got rid of the off-diagonal terms and leaves you just with the diagonals. All right. I mean, let's try to do this. I'll give you one to work on for a second. or coach me through it. Suppose I gave you now in 3 variables. Here we go. So instead of writing x, y, z, I'll use subscripts just to drive you nuts. x1 squared plus 6x1, x2 minus 2x1, x3 plus 11x2 squared plus 2x2, x3 plus 9x3 squared. So there's a nice, simple quadratic function.
Thanks. This is like my second.
And lest Dan rail at me, this is not a strip of Q, this is a 2.
I don't know the difference anymore.
How many of you want to complete the square and how many want to do the linear algebra?
I want to
That was only 2 votes.
drop the class.
Drop the class and go back to 8th grade where you learned to complete the square.
I can complete this.
All right, so what's the symmetric matrix?
1, 3 minus 1.
Everyone following what Tim's saying? That's on the diagonal. You're splitting the x1, x2 stuff into 2 equal pieces. You're splitting the x1, x3 stuff into 2 equal pieces. 1, 3, 1, 3, right? It's the exact entries of the matrix.
You want an 11.
What's happening here?
11.
1, 1, 1, 9.
There you go.
Wow. That was. That's too hard. That was. Yeah.
All right, let's go.
Let's go.
Tell her. You're gonna get E.
So let's start reducing and then we'll bookkeep. What am I going to do first? Add -3 to the first row
0, 2,
to the second.
0, 2, 4.
What's here?
4.
4.
4, yeah.
And now I'm going to do what to the third row?
Just add 1. 0 for
Add
E.
them together.
So what matrix did that?
Oh, yeah, some more
1, 0, 0, -3, 1, 0, 1, 0, 1.
So I'm again getting lazy and not putting all the zeros in the upper right. So we kept the rows the same, but then added -3 times the first to the second, and added 1 times the first to the third. So that's my first bunch of row operations. What am I going to do with this?
You reduced the last
Just
row.
need to.
Yeah.
We just put a negative
Yeah.
What happens?
It goes
It
down.
goes to 0, doesn't it?
0, yeah.
I wonder what that means.
Probably something evil.
What's the elementary matrix that I did here?
It's like it's like the identity matrix with a -2 right in the bottom middle. Yeah, like that.
So I need, so I started with A. I first did E1 to it. I then did E2 to it, and I got this guy, right?
Yes, right.
I want to solve for A. So what do I have to do?
E2 times E1.
Yeah,
I need inverses. But what do I have to be careful about?
Order.
The order.
So you could either
do
multiply-
inverse first, and then you want.
Yeah, suck shoot.
Could you potentially just multiply E2 times E1 and take the inverse of that? Which is
You could,
Let's do
but that's harder.
Really?
Because then you're going to have to do your super augmented matrix to find the inverse. My shortcut for saying inverse of elementary matrix is obvious by undoing the elementary operation That works for that matrix by itself and that matrix by itself, but if you multiply them, you can't do the shortcut. You're going to have to do the long way.
Slunk.
Well, let's try it. So I'm saying that you should have A is E2, E1 inverse times the echelon matrix. And I'm saying this is E1 inverse, E2 inverse in that order. So what's this matrix E1 inverse, E2 inverse? Well, I'm saying to undo adding -3 times the first row to the second, you add +3 times the first row to the second. And to undo adding 1 times the first row to the third, you do -1 times the first row. And then I'm saying to undo E2, I should just have what? A +2 there. Coming?
No.
So Matthias, have you multiplied
Yeah.
E1 and E2?
Yeah.
Okay, I'm going to get back to you in a sec. Good. So now we're going to multiply these. What do we get? Well, remember, the way to think about it is you just do these row operations to this matrix. So 1, add 3 times the first row to the second, add -1 times the first row, plus 0 times the second row to the third row. All right. So that's my L. Now, so Matthias, you're going to tell me what was E2, E1?
I got 1, 0, 0, -3, 1, 0.
+1, -2.
What? 7, -1, 1.
7?
Yeah,
It's not
-1,
quite right.
1.
Do we believe him?
No.
E2 times E1. Yep, he's right.
Because the negative.
Now, do you see any way to get from this to this easily?
No.
I guess not.
So how are you going to have to find the inverse of this guy? You're going to have to do the super augmented matrix. Whereas I was able to, I still had to do a matrix multiplication, but then I was done. This came as a great shock to me when I first understood this like 10 years ago. It wasn't, so I was actually writing a linear algebra book that I understood this. So this is not so helpful. It's more helpful to do the other way. All right, so I've got my L. Here's L, but I'm supposed to try to write A as L, D, L transpose, and all I've got is A is L times U. Where did U go?
I'm right here.
Where art thou gone?
So the last one is your
What should I do? He asks.
Break U into D L transpose.
Right, break this into D, L transpose, and notice L transpose is very much sitting there waiting for you to do this. What goes here? What goes here?
2,
And what goes here?
0.
0. And there's your D. So here's L, D, L transpose.
Wait, how is L transpose have? Oh, transpose. No. Oh, sorry.
You okay?
Yeah.
So you could do the completing the square by just the high school algebra stuff, And you would see that exactly you're grouping x1 plus 3x2 minus x3, squaring it, correcting the stuff, and then getting plus 2 times x2 plus 2x3 quantity squared. And that's what that output is. So you could do this from the completing the square and you get exactly that formula. Now I want to make one comment, especially if you want to look at the book. There's a way that's quite useful, and we'll see this again in a few weeks. The same idea is going to come up, of thinking about splitting this up where you're taking diagonal entries of D times the columns of L, and then the column transpose. I columns of L. So this looks scary to you, but I'm going to just show you what's going on. So let me do this example. Let's take this example. Well, maybe I'll just do the 2 by 2 one that's left up there first. We still have we had, what was the original matrix? It's gone. 3,
-6.
-6, -6, 11, we said was, L was 1, -2, D was 3, -1, and then L transpose. Okay, there's L, D, L transpose. Now here's what I'm going to claim. And we're going to use fingers and check it. This is the same thing as taking this number times this column, this row. So 3 times 1, -2, 1, -2 transpose. Plus this number times the second column times its transpose. Well, let's check it out. What do you get when you multiply these two things? You get 1, -2, -2, 4. What do you get when you multiply these two things? 0, 0,
0, 1.
0, 1. So is it working? You're getting 3 times 1, -2, plus -2, 4 multiplied by 3, so it would be -6, 12, and then adding the -1 in that slot. So you're breaking this matrix up, but we're thinking about multiplying this product out as a sum of 2 terms, one for each diagonal entry corresponding to the appropriate row, column, and row here. If you think about it, that's exactly how this matrix multiplication works out. If you want to pick any entry here, you're going to get it exactly by finding the corresponding entry here as doing an appropriate combination of entries here with entries there. Just to perplex you further, let's do the last example now. So our last example was, where did A go? Up there. 1, 3, -1, 3, 11, 1, -1, 1, 9. All right, so I had my L here, D, L transpose. I'm supposed to split it into 3 pieces corresponding to the 3 entries of D. Right? That's the first one. Then I have the second one, which goes with the second column and the second row. And then it's sort of stupid here, but I have the third one, which is stupid because it's 0, so I'm not going to see this stuff here. So I'm saying that this breaks down to 1 times the first column of L times its transpose, plus 2 times the second column of L times its transpose, and then lastly plus 0 times the third column of L times its transpose. So you're breaking your linear map, your symmetric linear map, into 3 pieces, 1 for each slot in the diagonal matrix. So this is the piece that corresponds to the first sum when you do the quadratic function as a sum of squares. This is the piece that corresponds to the second sum, second term, and this is the third term. So, lucky for you, you get a couple of web work problems to practice doing this. And what I'm going to end with is just some terminology. It's nothing particularly fascinating, but there are words that go with what we want to do when we want to see the nature of the critical point. So, we say quadratic form, so that's this quadratic function polynomial we've been looking at, Q, is positive, semi-definite, or not with the semi, or negative, semi-definite, or not with the semi. So positive definite or positive semi-definite, and then indefinite if positive semi-definite means that the Q of X is always positive, and in the semi, except for 0, of course. And the semi allows you to put or equal to 0. And the semi-definite would mean that it is 0 for some non-zero vector. Do you have a guess whether one of these examples was positive semi-definite?
It's greater than or equal
The first one, second one.
First one. We've done 3.
The second one. The first one.
The second one has a positive and a negative. That's going to be indefinite. Q of X is positive for some x's and negative for some other x's. That's indefinite. That's what this one was. This guy is positive semi-definite because of the 0 here, but these are positive. And negative, you just switch this to this and then put an or equal, blah, 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 blah. What's the tip-off? Positive definite, all the diagonals are positive. With the semi, you would have some diagonal 1 is 0.
So it just means it's like contained, like the graph is contained within the positive.
Yep.
Range or the negative.
Yep. These, they're all negative, except for the semi, one of them vanishes. And for the indefinite, at least one D is positive, and at least one D is negative. Okay. So you're going to see that this then is going to allow us to decide whether we have maxes, mins, or saddles once we apply this to the calculus. Okay, onward on Friday. have not quite covered everything you need for all the web work yet, but I will finish it on Friday.